since this end is connected to the positive terminal and this end is connected to the negative terminal, so the free electrons present in the wire would be attracted towards the positive end and would be repelled from the negative end. So they would start flowing in this direction in the wire. But the conventional current is the current which flows opposite of this movement, so that would be from positive to negative. The part of Jk that is in the magnetic field experiences a force F. So this is what we call the motor effect, that whenever a current carrying wire or a conductor is placed in a magnetic field, a force acts on the conductor because of the interaction of both magnetic field. State the direction of F and describe how this direction is deduced. So in generators, right hand rule is used, and in motors or motor effect, the Fleming left hand is used. So the first finger would be aligned into the page. The conventional current is to the right, so the second finger would be aligned towards the right and thumb is pointing downwards. So it means that a force in the downward direction would be experienced by this conductor. Question number 9 says figure 9.1 shows a permanent magnet lying on a piece of paper. So this is the piece of paper and it is the permanent magnet lying on this paper. Underline the material in the list from which it is possible to make a strong permanent magnet. So a strong permanent magnet is made using a steel. Describe an experiment to plot the pattern and the direction of the magnetic field surrounding the magnet. You may draw on figure 9.1 if you wish. So the first thing is a plotting compass or the magnetic compass is to be used. So for example, the compass is placed here near this end to check whether it is a south pole or a north pole. So the compass is pointing like this away from the pole. So it means that it is the north pole and this is going to be the south pole. Now the direction in which the compass is pointing, a dot would be made, and then the compass would be placed again such that the tail of the magnetic compass needle is aligned with the dot, and the direction in which the arrow is pointing, another dot would be made, and then again the compass would be used, aligning the tail of the arrow with the dot, and the direction in which the arrow is pointing, a dot would be made. And this process would be repeated such that we obtained many dots, and starting from one end we reach to the other end, and when we connect these dots we get a loop, and the direction shown by the arrow of the magnetic compass, it would be the same as the direction of the magnetic field. And this process is repeated several times so that many loops are drawn, and this is how the magnetic field of a permanent magnet is drawn using this plotting compass. I'm writing the answer. A plotting compass would be used by placing it next to the magnet. A dot would be marked where the needle points. The compass would be moved so that the tail of the needle is aligned with the dot, and the next dot would be marked where the needle points. The marking continues and loops or lines would be drawn. The needle points in the direction of magnetic field. So this is the description of the experiment with which we can find out the direction of the magnetic field. Other way of doing it could be using the iron fillings, and they could also be used to draw the pattern of the magnetic field around a permanent magnet. The next part says figure 9.2 shows the north pole of a magnet placed in front of the south pole of a second magnet. Now this is the north pole and this is the south pole. A section of a horizontal metal wire JK lies in the magnetic field between the two magnetic poles. So this is the section of the wire. End K of the metal wire is connected to positive terminal of a battery and end J is connected to the negative terminal. So this is the positive terminal connected end of the wire, and this is connected to the negative terminal of the battery. So it means that a current would start flowing through this wire in this direction. The direction of the conventional current would be to the left. Explain in terms of electrons why there is a current in the wire and state the direction of the conventional current. So the currents flowing is to be explained in terms of electrons. And secondly, the direction of the conventional current is to be mentioned here. Since this end is connected to the positive terminal and this end is connected to the negative terminal, so the free electrons present in the wire would be attracted towards the positive end and would be repelled from the negative end. So they would start flowing in this direction in the wire. But the conventional current is the current which flows opposite of this movement. So that would be from positive to negative. So conventional current would be from positive to negative in the left direction, and the electron flow would be from left to right direction, from away from the negative polarity and towards the positive polarity. So I'm writing free electrons are attracted to positive terminal and repelled by negative terminal, and move to the right, while conventional current flows from K to J. Since K is at positive polarity and J is negative, so the conventional current would flow like this. The part of Jk that is in the magnetic field experiences a force F. So this is what we call the motor effect. that whenever a current carrying wire or a conductor is placed in a magnetic field, a force acts on the conductor because of the interaction of both magnetic field. State the direction of F and describe how this direction is deduced. Okay, so the direction is deduced by using the Fleming left-hand rule. So in generators, right-hand rule is used, and in motors or motor effect, the Fleming left hand is used. Index finger points in the direction of magnetic field. Then second finger is aligned with the current, and thumb gives the direction of F, the force exerted on the conductor. Now in this case, the magnetic field is from north to pole. It is always from north to pole, so the first finger would be aligned into the page. Then the conventional current is to the right, so the second finger would be aligned towards the right, and thumb is pointing downwards. So it means that a force in the downward direction would be experienced by this conductor. So I'm writing the direction. The direction of F is downwards or down the page in the above scenario. So this is how we can find the direction of the force acting on the conductor. Now, the next part says the equipment in figure 9.2 is used in a similar experiment. The part of JK that lies between the poles of the magnet now passes through a long iron tube. So a long iron tube is surrounding the wire that is fixed in position and it cannot move. The tube is shown in figure 9.3. JK is connected to the battery in the same way as before. State what happens to the force F on the wire. Explain your answer. Since the wire is placed in an iron tube, so iron is a material which provides a very convenient path for the magnetic field lines to pass. So all the magnetic field lines would pass through the iron material coming from North Pole and would go towards the South Pole. And no magnetic field or field lines would interact with the wire. So since there is no interaction of the magnetic field lines, so there is no force acting on the wire JK. So I'm writing there is no force F on the wire, and the reason for this is that because the wire is magnetically shielded by the iron tube. So iron tube is the material from where the magnetic field lines would be passing, and there would be no interaction between the two magnetic fields now. The next part says the iron tube and the wire are removed. A square vertical coil is placed between the poles. This is the square vertical coil, so that the plane of the coil lies in the magnetic field in figure 9 point, as shown in figure 9.4. So this is the coil now, and north pole, south pole. Now the square coil is placed in the magnetic field. Explain why the coil tries to rotate when there is a current in the coil. Again, this is because of the motor effect. So the first thing is, when there is current in the coil, when a current flows through the coil, there is a magnetic field around the coil also, and since it is placed in the magnetic field of another magnet, so both the magnets magnetic fields interact, and there is a force on the coil which tries to rotate it, which tries to create a moment in the coil. So the first thing is, coil produces a magnetic field around it. The magnetic field interacts. This magnetic field interacts with the magnetic field of the permanent magnet, and force acts on the coil such that opposite poles of the two fields attract, and like poles repel, producing a moment in the coil. So that is why it tries to rotate when it is placed in a magnetic field.